Hi, I'm Ben-Yaakov. This presentation is entitled What is Q in LLC Converters? This is an appendix to an earlier video that I've posted, which is entitled The Confusing Definition of Q in LLC Converters. Here is the link to the earlier video. I'm also going to print this link at the YouTube page of the video that you are now watching. In the earlier video, I was concerned with the LLC converter. Here I am showing a half bridge, two inductors, capacitor, rectifier, filter capacitor, and a load. And the point was that normally it is sort of customary, I should say, to represent the response of the LLC converters, output over input, this way. Here we have quality factor, and here we see 0.5 to 0.1. And what I was actually pointed out in the earlier video, that it is kind of strange because we are used to have a high gain at a high Q, and here it goes all the way around. Now I've shown that there is actually a misconception here, a mistake I would say, in that the Q is related in this particular presentation, which is very customary. This is always you'll find in, say, application notes and papers. This Q is related to the series resonance of the unit, that is this resonant here, between here and here, while in this region the LLC behaves like actually a parallel resonant converter. And therefore, you have to use a Q which is related to a parallel resonant converter, nor a series resonant converter. Once you do this, everything comes up to be okay, because you see the Q is going up, the gain is going up. Actually, there's a matching between Q and the gain. Everything is fine. So this is the point of the earlier video. I also pointed out that in this region, you cannot work as an LLC because the slope here of the gain is not constant, and therefore there is some ambiguity here as to whether you have to increase the gain or reduce the gain if you work in this area. So you cannot work in this area as an LLC converter, and therefore they say if you are using Q sub S, you are limited to 0.5 or maybe 0.2, and this is the region that you like to work. You cannot work here. Following the posting of this earlier video, I got some reviews and actually criticism, and I'm pointing out to three major issues that was brought up. One is there is no parallel resonant converter in LLC. That is, and no matter at what frequency range, this is not a parallel resonant converter. Another point that was made is that the Q at the low frequency should be expressed like this. These are the two inductors. This is the characteristic impedance over RE, and not RE over this characteristic impedance as I suggested in the earlier video. Okay, this is one over the other. So either this is correct or this is correct. Both can't be correct. Obviously, you can define Q as you wish, but the question is what is the correct way to do that? And then there was another point that was brought up, that if we said that the Q has to be smaller than 0.5 for operation as an LLC, then therefore there is a corresponding resistor to this Q, and which means that you can never achieve a lower gain with this, in this case when RE is small. So in this presentation, I'm going to very briefly go over the previous video, main points of the previous video, and then to talk about the fundamentals of quality factor concept, because there's an issue here. What is the quality factor? So we have to step back and ask ourselves, what is quality factor? And then we'll be able to answer which expression is correct. And then I'm going to rebuttal the criticism. Now, in the earlier video, I've shown that there are a number of resonant converters available or have been published or described. This is the equivalent circuit based on the small signal or first harmonic approximation and with the RE concept that is describing the nonlinear load as a linear resistor according to Professor Steigerwald. And we recognize a series resonant converter in which the load is in series. We have a parallel resonant converter in which the load is in parallel to either the capacitor or the inductor. This is actually called a parallel loaded resonant converter. The loaded is normally dropped. So when we say parallel resonant converter, we mean one of these. And then the LLC, which is a multi-resonant, in which again we have the resistor, the REC resistance representing the load in parallel to Ln. I pointed out that one way to understand the operation of the LLC, here the LLC, complete LLC, is to sort of break the frequency ranges into two ranges. One is the low frequency, one is the high frequency. So you can say that since this inductor is smaller than this, you can neglect it as a first approximation, and then you add up with a parallel resonant circuit, or parallel resonant converter, I should say. And here, at high frequency, you can sort of neglect Lm because it is a higher impedance than R sub E, and therefore you get here a series resonant converter. And then I discussed what happens in the region of the low frequency. The low frequency, we have a parallel resonant converter, and therefore the Q, the quality factor, is Re over Z or Re over omega 0 Lm. And once you define it this way, this is consistent with what we have here, and we see it as the Q goes up, the gain goes up, everything is fine, and we are talking about this region here. This is the low frequency region. So the first claim that was made in criticizing my earlier video was that at low frequency, it is not a parallel resonant converter. It is a series resonant converter, claiming that parallel resonant converter is something like that. You have a parallel C and F and RE in parallel, and therefore the impedance at resonant is high, while here in the actual LLC, the impedance is low at resonance, and this is not a parallel resonant converter. This is what was claimed and criticizing my approach. The point is that there is a sort of a misconception here and not recognizing the literature and what is already accepted and used for many, many, many years, and that is that this configuration of a resonant converter in which you have the RE in parallel to the capacitor or the inductor is called a parallel resonant converter. The actual correct name would be parallel loaded resonant converter, but this loaded is normally dropped, and when we say now today parallel resonant converter, we mean these. This is what we mean, not this. This is what we mean. And we can go back to the very early development of this whole technology and the pioneering work of Professor Erickson, and this is a paper by Professor Erickson and at that time his PhD student Johnson. It's called Steady State Analysis and Design of the Parallel Resonant Converter. It's in 1988. And here it is. What you see here is a series connection of LLC, and the load is in parallel. This is what is called parallel resonant converter. That's what it is. It should have been parallel loaded resonant converter, but as I've said, this is what is already accepted. So we call this a parallel resonant converter. In this case, it's in parallel to the capacitor. We are talking about parallel to the inductor. Well, I'm not going into this issue. Why is it that you don't see that many converters with the parallel to the inductor? This is not the issue of this presentation. Maybe I'll talk about it in another video in the future. So this is not what we are talking about. In fact, if you would have had this circuit, you cannot feed it with a voltage source because then you are killing the resonant. So you need a current source for this kind of a configuration. And this is probably why this type of converter is not that popular. And there aren't many papers that describe such a configuration. In fact, I did some work in this area. I have a number of papers of this type of a converter. One of them is from 1993, and it's called capacitive loaded push-pull parallel resonant converter. And in this case, here you have a sort of push-pull, and here you have indeed a inductor and a capacitor. These are here, and they are loaded in parallel by the load. So this is indeed a parallel connection of an inductor and a capacitor, but here you do need to have a current source, which is done by this push-pull and this inductor at the input. So this is also sort of a parallel resonant, but as I've said, in the literature today, when one says parallel resonant converter, this is what is meant, usually, okay? Maybe there is some confusion here, but that's the fact. That's the way this is the term that is used. So therefore, the statement that there is no parallel resonant in LLC is incorrect, because this configuration at low frequency, when I've sort of eliminated L sub R, is what we today term parallel resonant converter, okay? And the paralleling here is between the load and L sub n. And then I'm going into the question of what is quality factor for the next step. Well, looking at Wikipedia, we find that quality factor is defined as the ratio of the initial energy stored in the resonator to the energy lost in 1 radian of the cycle of oscillation. Meaning that this is the ratio between the reactive power and the real power, okay? And reactive power, of course, is switching between the inductor and capacitor, so we just talk about, say, the inductor. And the reactive power here is, since these have the same voltage across them, this is the paralleling effect, it's V squared over omega 0 Lm. This is the reactive power. This is the real power. And here is the ratio between them. And of course, omega sub 0 L, you can replace it by the impedance, and we get the Q is Re over Z. Z is the square root of Lm over Cr. Okay? So Q is either this or this. This is from the fundamental concept of quality factor, reactive over real losses. Now, therefore, the proposal that Q should be defined this way, which is Z over Re, while I'm saying that it should be stored energy over dissipated energy, it comes out to be Re over Z. So this is just not consistent with the concept of quality factor. What is quality factor? This is quality factor, and it turns out to be this expression and not this expression for a parallel combination. This will be for a series resonant, but for a parallel resonant, as we have here, this is the correct Q term. Another issue that I like to show here is how good is this approximation that I'm doing? Is it really holding any water here? So what I did here, I'm showing actually 3 simulations, 3 circuits representing a LLC converter. Here we have the 2 inductors, the load, and the capacitor. In here, I've eliminated, here I showed it like here, showed it this inductor. And here, I've sort of crossed out this Lm, taken it out, assuming that it's a high impedance. So this is for the high frequency. This is a series resonant. This is a parallel resonant converter. And here it is. So this is the full simulation. And this is the approximation. Well, obviously it's not the same, but it's pretty good. It's pretty good. Using the concept of parallel resonant, assuming that at low frequency, this Lm, L sub R. This is for a ratio of 6 between Lm and L sub R. As for the series case, well, at this range, it's almost no response here. We now come to the third point of the question of whether we can get a gain or we cannot get a gain. So I'm going to answer it by actually showing a real design problem. In fact, this is a problem that I'm now dealing with in a real system that we are designing, and here it is. This is given. This represents actually the inductors which are actually part of the transformer. This is actually the leakage, and this is LM of the transformer. So this is given. You cannot change it. This is a given transformer that you have to use. Also, the RE is given because you need a certain power. You have a certain V in, so RE is given. You cannot change it. Now, since the voltage at the input can change in the ratio of 1 to 2, you like to have a gain of 1 to 2. Now, we would like to have the frequency in the range of 100 kilohertz, and maybe a little bit lower than that, certainly not much higher, and certainly not much lower. Okay? So this is a given problem. So now, I'm finding for this particular case, with this resistor, 6 ohm, these inductors, and for the 100 kilohertz, what is the Q? And I find that the Q sub S is 1. This is bad. This is not compatible with the LLC requirements for gain. That is, we are in this region, which, as I've already mentioned, this is not an operating region for LLC. You have to have Q sub S small, like 0.2, and smaller, or Q sub P high. So there seems to be a problem here. And indeed, if I look up the response, this is what I have. Well, I cannot change it. If I could have changed RL, I could have gotten into this low frequency region with gains, etc. But with Rn given as 6 and the inductors that I have and the frequency that I've chosen, about 100 kilohertz, I cannot use this circuit as an LLC converter. That's the fact. So what can I do? Well, what I can do, I can use it as a series resonant converter. I'll set this point as the operating point, and therefore I can have a gain of 2 if I wish. I can also have some more attenuation going to a lower frequency. I need quite a bit of a change in frequencies. This will be, as you can see, between, say, 250 to about 150, so 1 kilohertz, a lot of change, which is worse than in the case of LLC. This is the fact. This is what I can do when I'm restricted to the particular inductances and the load which is given. Okay? That's the way it is. Now, suppose I like to work it as an LLC. So what do I have to do? I have to make sure that the Q sub S is smaller than 0.2. And this allows me to find what is the F sub 0, the resonant frequency, the highest of the resonant frequencies, 20 kilohertz, not great. This brings me to a capacitor of 2.5 microfarad. And here it is. Well, I found that 2.5 microfarad is kind of marginal, so I've put here a 10 microfarad. And in this case, I'm getting the LLC response. This is the gain of 1, like somewhere here, which is fine. And then I can have a higher gain, more than 2, which is what I need. I probably could put a smaller capacitor here. But this is not satisfactory because I cannot work at this low frequency. The transformer, for one thing, transformer will not be able to cope with this low frequency. It will saturate. So therefore, you can see that given these inductors in the frequency range that you like to work at, sometimes you cannot accomplish an LLC operation, and you have to resort to a series resonant converter, which is fine, but the span of frequency will be a bit higher. So let me go back now to the 3 points that were raised. number one, that there is no parallel resonant converter in LLC. Well, as I've shown, there is a parallel resonant LLC. In fact, it should be said that it's a parallel loaded resonant converter, and this is what is now accepted in the literature and among the workers in the field. And also, I've shown that this expression for the Q at the low frequency is just inconsistent with the concept of quality factor, which is the reactive power over the real power, and this leads to this, which is 1 over this thing. And then I've shown that indeed there is a restriction. It's not that you cannot get gains, but you cannot operate the system as an LLC. You can operate it as a series resonant converter, which is fine, can give you pretty good results, but it has a sort of limited performance as compared to the LLC. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.